Hello there. Today, let's have a look at some past paper questions from the third part of the radiation unit in National 5 Physics, nuclear reactions and nuclear power. So, question number 1. A student makes the following statements about the fission process in a nuclear power station. Firstly, electrons are used to bombard a uranium nucleus. Secondly, heat is produced. And thirdly, the neutrons released can cause other nuclei to undergo fission. Which of these statements is or are correct? Pause the video and see if you can work it out. Okay, so first of all, electrons are used to bombard the nucleus is not true. It is neutrons which are used to bombard the uranium nucleus. Heat is produced, and the neutrons that are released can go on to collide with further nuclei, causing further fission reactions. That is true. So 2 and 3 are correct. Answer E. Number 2. We have a passage here with missing words which we need to fill in the blanks. I'll pause this and you can try and work out what words should fit in the blanks. Okay, so during a nuclear fusion reaction, two nuclei of smaller mass number combine to produce a nucleus of larger mass number. During a nuclear fission reaction, a nucleus of larger mass number splits into two smaller nuclei of smaller mass number. Both of these reactions are important because these processes can release energy. Therefore, the answer is E. Question 3. In a nuclear reactor, a chain reaction releases energy from nuclei. Which of the following statements describes the beginning of a chain reaction? Pause the video and see if you can work it out. Okay, so the beginning of a chain reaction occurs when a neutron is fired towards the nucleus of a large atom, causing it to split, releasing energy and further neutrons, which can then collide with further nuclei, creating further fission reactions. So the answer, therefore, is E. A neutron splits a nucleus, releasing more neutrons. Number 4. Another passage with some blanks. Pause the video and see if you can work out what these blanks are. Okay, so during a nuclear fusion reaction, two nuclei of smaller mass number combine to produce a nucleus of larger mass number. These reactions take place at very high temperatures and are important because they can release energy. So therefore the answer is B. Question number 5. Nuclear reactions are used to generate electrical energy in a nuclear power station. The fuel for the power station is in the form of pellets containing uranium-235. A fuel pellet has an activity of 80 kilobecquerels. State what is meant by an activity of 80 kilobecquerels. So, we need to understand first of all that activity is the number of nuclei which decay per second. So, if the activity is 80 kilobecquerels, that means 80,000 nuclei are decaying per second. Part B. In a nuclear reaction, a uranium-235 nucleus is split by a neutron to produce two smaller nuclei, 3 neutrons, and energy. Explain how a single reaction can lead to the continuous generation of electricity. So, The neutrons that were produced in the first reaction can then go on to collide with further nuclei, causing further fission reactions to occur, and so on. This is a chain reaction. Part 2. One nuclear reaction releases 3.2 times 10 to the power of minus 11 joules. In the reactor, 3 times 10 to the power of 21 reactions occur each minute. Determine the maximum power output from the reactor. Okay, this is a tricky question because it sort of straddles the electricity and energy unit and the radiation unit and isn't a typical formula style question. What we need to look at here is we know how many reactions are occurring each minute, and we know how much energy each reaction produces. So therefore we can work out the total energy being produced each minute. Okay? So the total energy is the energy of one reaction multiplied by the number of reactions, which is 9.6 times 10 to the power of 10 joules per minute. Now, we want to work out the power output. Now, the power is the energy being converted per unit of time. So, power equals energy over time. The total energy being released each minute is 9.6 times 10 to the power of 10 divided by 1 minute, which is 60 seconds. And that gives us a power of 1.6 times 10 to the power of 9 watts, or 1.6 gigawatts. Okay, so that brings us to the end of some past paper questions about the nuclear reactions and nuclear power part of the course. I hope you found this useful, and I'm sure I'll talk to you again after a while. Bye for now.